Hi everyone, my name is Pradyumn Kejriwal and today we will discuss the solutions to the 16th problem from the CP sheet by TLE Eliminators under the rating of 1400. So let's begin. As you can see, I have my sheet right here and I can open this problem. Alright, so it is called Arranging the Sheep. You are playing the game Arranging the Sheep. The goal of this game is to make the sheep line up. The level in the game is described by a string of length n consisting of the characters dot, empty space, and star, which is sheep. In one move, you can move any sheep one square to the left or one to the right. If the corresponding sheep, if it exists and it is empty, right, we cannot move this sheep to the left because there is no empty square to the left, right? The game ends as soon as the sheep are lined up. That is, there should be no empty cells between any sheep. For example, if n equals to 6 and the level is described by the string star star space star space space, then the following game is possible. Okay, so they have just made something like first they moved this to the right, then they moved this one to the right like this, and then they moved this to the right, and then finally after doing all of this they reached here, right, where all three of the sheeps are lined up. Okay, for a given level, determine the minimum number of moves you need to make to complete the level. So to complete the level, that means we have to line up the sheep. Okay, so yeah, basically I'll just repeat the problem. I'll just, in my own words, that you have been given a farm. Okay, and on the farm, it is of length n and there are some sheeps. So let's say there is a sheep here, a sheep here, and a sheep here. Okay, and you have to basically do some moves, that is either move it to the left or to the right, so that finally all of the sheeps are together, there are no gaps. So in this case you can just move one sheep here, and as you can see that these three are in line. Okay, so in this case the answer would be 1, right? So yeah, it is pretty simple. The problem is pretty simple to state. And in the samples we have, here you can see that in this case the star is sheep. Okay, the star is sheep, so you can just move this one to the left one step, so the answer is 1. Then for this case all sheep are already lined up, right, so it is 0. Then this one only has one sheep, so it is lined up already, of course, so that is also 0. And this has no sheeps, so it is 0 again. And the final one, it is 9. Okay, so why it is 9 I'll show you later. Okay, but for now the samples are like this, you can just see, and the constraints on n are up to 10 to the power 6, right? So basically, since we know that in 1 second we can do up to 10 to the power 8 operations in a single test, right? So if your n is up to 10 to the power 6, then maybe you can pass O of n or O of n log n. Okay, but not like O of n square. Okay, or even O of n log square n might also not pass in this, because if you calculate it will exceed the 10 to the power 8 limit. Okay, so yeah, now you can just pause the video and try to solve the problem by yourself. Alright, so I'm assuming now that you have tried the problem by yourself. Okay, so first of all, what we can do in this problem is that we can observe some things. Okay, let's say we have a test case right here. Okay, like this kind of, let's say we have 7 blanks and we have 3 sheep like this. Okay, we have these sheeps and we want to find the answer, right? So since finally we want that these 3 sheeps have to be together, right? So what can the final positions be? It can be like this also, maybe like this, right? These 3 sheeps are here in the first 3 blanks, or maybe it can be like this, right? Or maybe it can be like this, and so on. You get the point, right? Like this or like this, right? So you have these possibilities, and out of them you want to select the most optimal one, so that it takes the minimum number of moves to reach that. Okay, but how do we actually calculate that to reach a certain position? How many moves do we need? Like let's say that I knew that this is my final state. Like for my optimal answer, this is my final state. Then how can I actually calculate the answer? How do I do that? So for that you can observe that, see, this sheep has gone here, this sheep has gone here, and this sheep has gone here, right? So basically we know the starting and the final positions of this sheep, right? So we can just take the distance, that how much they walked. Like this sheep walked 0, right? It is there where it was at the beginning only. Then this sheep moved 1 to the left, right? So that one move right here. And this sheep moved like how many? 1, 2, and 3. It moved 3 units to the left. So the final answer would be 4 if we knew that this was the optimal state, right? So like we calculated the answer assuming that this is the optimal final state, right? But let us try another one. Okay, like let's say it was this. Like what is the answer for this? Okay, so in this case, like this one moved a single time, right? Then this one moved 0 times, and this one moved twice, right? So in this case the answer is 1 plus 0 plus 2, which is 3, right? And in the previous one we were getting 4, so of course 3 is better, right? And in this case I can guarantee you that 3 is the actual answer. Like I will tell you why I'm saying that, but for now you can just trust me that 3 is the actual answer. Okay, so basically if we knew that what is the final state of these sheeps, we can simply find the answer using that. Okay, but how do we actually check that what is the final state of our sheeps? Like what is the most optimal way to arrange those sheets? So for that it is more intuition and less proving. Like to prove your logic you will need actually a very, like not very tough, but the intuition is a bit easier for that. Like if you just get the idea and you guess the solution, it might work. Okay, so in this case the intuition is more important than the proof, but of course I'll give both of them. So in this case, to give the intuition for this, let us try to, like I'll try to make one more test case. Okay, so let's say we have these blanks and there's a sheep here, a sheep here, and a sheep here, right? Now let's say we try to find the answer. So one possibility is that I bring these two sheep there, right? So in that case, what is the answer? Like final state, if it is this, then the answer is what? So this sheep moved 1, 2, 3, 4 times, and this sheep moved 1, 2, 3, 4 times. So the answer would be 8 in this case, right? But if we tried this thing, okay, then it would be just 1, 2, 3, and 4. So this sheep moved 4 times, and therefore the answer is just 4 if we take this final state, right? So you might be tempted to just consider that wherever there are more sheep, just move the other ones towards that, right? So that is kind of heuristically correct, but like it is not very rigorous, right? Like in this case we knew that our sheeps were in 2 groups and we just moved the smaller one to the bigger one. But what if those sheeps are not in 2 groups, right? So we just have to generalize this idea. Like how do we generalize this for multiple groups? Okay, so for that I'll give you one more example. Okay, just bear with me. Like let's say we have two sheeps like this, one sheep like this. Now one idea is maybe we'll try to bring these two sheeps towards here. Okay, so in that case this one will do 2 steps, right? And this one will reach here, so it will take 1 2 3 4 5 steps. So the answer is 7 if I bring it here. Now if I bring these two, like if I assume that for my final state is this towards the left, then the answer would be what? Let's say 1 2 3, right? And 1 2 3 4 5. So it is 8. So in earlier one we were getting 7, and it's this one we are getting 8. But let's try one more thing. Like let's try to keep them near the center. Like this S is in the center, right? So we'll try to keep them near the center. So basically I'll try like this. Okay, so in this case we'll get 1 2 and 3 and 1 and 2. So we just get 5 moves, right? So you saw that when we tried to move them here, we got 7 moves. For here we got 8 moves, but in the center we got just 5 moves. Okay, and that's because from both sides they have to, like, the total amount of distance that they traveled was lesser, because in both sides they need to travel less amount of time. Like if you have some points, okay, and you want to make them together, what you will try to do is you will just try to bring all of them to the middle point, and that will actually minimize your total distance that they travel. Okay, and that's the intuition here, that you will try to move all the points towards the middle point. Okay, so move all sheep towards middle sheep. Okay, and this is optimal. Okay, and why it is optimal, I can actually tell you that by using an example. All right, so let's say we have 7 sheeps, or let's say we have 5 sheeps. Okay, so they are at positions A1, A2, A3, A4 and A5. So basically they are at these positions. Okay, like these are their coordinates. This is A1, so I have drawn them on a number line. All right, and my claim is that I'll move these points toward the center, right? So I won't move this center, right? So my claim is that I won't move this center. So how do I prove that claim? So the proof is that by contradiction. Like let us assume that we move the center. Okay, like let's assume we have moved this by 1 toward here. Okay, all right, we have moved this point towards 1, like towards the left side by 1, right? So this sheep is here now. So now if this distance initially was d2 initially, like, okay, so after moving this, what has it become? It is d2 minus 1 now, right? So basically a2 has to move just d2 minus 1 steps now, right? And if this distance initially was d1, so now it has become like d1 minus 1 after a3 moved to the left. So now this a1 has to move only d1 minus 1, right? But what about this a4 and a5? Like initially they were traveling only this much distance, like let's say this is d4, but now they have to travel one more distance, right? Once more they have to travel, so now they have to travel d4 plus 1, and similarly for a5 it has to travel d5 plus 1. So finally the total amount of distance that it traveled is what? Like a1 traveled d1 minus 1 distance, then a2 traveled d2 minus 1 distance, then a3 it traveled one distance, right? We assumed one distance, so plus 1. Then d4, like this a4 traveled d4 plus 1 distance, and this a5 traveled d5 plus 1 distance, right? Essentially, since we moved this center point to the left, that means all the points to its right, they have to move one more step, right? Because we are going away from those points, so all of them would have to go one more step, right? So this is the entire expression here. Now you can see that we have two minus ones and these two plus ones, so they cancel out. But what about this plus 1? It is remaining. So basically, in this case, we got a distance of d1 plus d2 plus d4 plus d5 plus 1, right? And if we hadn't moved our a3, like if our a3 was there only, then our distance would just be a1, a2, a4 and a5. So like d1 plus d2 plus d4 plus d5. Okay, so if we had not moved a3, then our distance would be less. Okay, like here the total distance has increased by plus 1. All right, so that's why we always, like, we never move the middle one. Like, the intuition here is that if you move the middle one, then the amount of loss, like the amount of loss that you have, like the extra amount of moves that you do, is worse than the amount of gain that you get. Like here, if you move a3 to the left, these 2 points which are to the left have to move one step less, but these 2 points have to move one step more, right? So there is no profit in doing that, and this one extra move costs us even more. So basically, you will not move the center point. And this proof is quite similar to the median proof. Like if you have numbers a1, a2 up to an, and you want to minimize x minus a1 plus x minus a2, like absolute value, okay, up to x minus an. If you want to minimize this sum value, you will take the x as the middle value or the median of this. So this proof also is quite similar, if any one of you know this. But yeah, this is the entire proof that we won't change the middle element. So essentially we know that what is the final state, right? And we can simply find out the number of moves to do that, right? So for example, for this test case, I'll just make it one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So S and S here, and S and S here as well. Okay, so as you can see that this one is the middle one, right? So we won't move this. So if we are not moving this, that means that this S will come here, and the two S's will come like that, and these two S's will come like this. So what's the distance? The distance is just this 3 distance plus 1, 2, 3, 4, 4 plus this 1 plus 1, right? So the answer is 9. 4 plus 3 plus 1 plus 1. So the answer is 9, and that is correct, right? So you just have to look at this greedy approach to not move the center one, right? All right, so this is the entire solution here. And like, just for some implementation details, like how to implement this, you can simply make a vector of positions. Like you can just keep track that on which indices are there sheaves. Like let's say on I1, I2, I3 up to IK, there are K sheaves, and these indices are there, and they are already sorted order. Okay, then the middle one, like I of K by 2, this one will not change. Okay, and the other ones will come toward it, right? So they will spend mod of I K by 2 minus I1. Like if I want I1, then it will spend I K by 2 minus I1. But actually it doesn't need to come to I K by 2. Like as you can see here, this was the middle one, right? So this S did not need to come to entire I k by 2. Like it had to just go to this index only, like 2 steps behind, right? Because we don't need all sheets as a single point, we need them contiguously. So we will just subtract the difference of these two indices. Like ideally, if I write this I k by 2 minus I1, then I am bringing this I1 to that I k by 2 wala point, right? But I can just make it, like I just need to make it some steps behind. And what is that some steps behind? It is the difference of these indexes. Like if you can see, this is I1, this is I2, this is I3, I4 and I5, right? So I just brought this I1 to I3 minus 2, like this is I3, and I brought I1 to here, so it is I3 minus 2. So basically, what is this 2? This 2 is just the difference in these two indices. Okay, so the final cost of bringing I1 to I k by 2 would be like the difference between these one minus k by 2 minus 1, right? And this is for the cost, and you can just add this up over all the indices. Like I took one here, but you will just take all of the positions where the sheep are and just add them up, right? So yeah, I'll just show the code now. So as you can see, in my main function I just have fast input output and the test cases, and in my solve function I am just taking the string, and I have this vector of int called sheeps which takes the positions, and for int I equal to 0, I less than n, I plus plus. If s of I equals to star, so if there's a sheep at that index, I am pushing back that index in my sheeps array. Okay, and then I am checking the middle index, so n by 2 essentially, right? N minus 1 by 2, because it is in 0 indexing, so I am doing n minus 1 by 2. And then finally the ans variable, which will store the total cost. So I am just iterating over all the sheeps, and finally the answer would be like I'll just add ans plus equals to sheeps of I minus sheeps of index minus index plus I, right? So like for all index I, for all indices I will add this up, and this index is the middle index, right? And I'll just print the answer. Okay, so this takes O of n space, because I mean this for loop is O of n time, because it is O of n, and this is also O of n time, and this takes O of n space because the number of sheets might be n, right? So the total space is O of n, and the time also is O of n for the solution, right? So I hope you understood this, and thanks for watching.